Okay, guys, so first of all, this worksheet is titled incorrectly. My bad. So it's not area on a base because we already have done area. We're looking at volume now. Okay, so it's volume on a base. So your learning goal, which you can copy off the backboard, is that you will be able to solve for volumes formed on a base. Okay, write that down. Solve for volumes formed on a base. Okay, so let's go ahead and get started then. So when you guys were building your volumes on a base, you had to measure some piece of your base, okay? Like you didn't just start by drawing random shapes or drawing a random square and hoping it would fit. Even if you didn't measure every single square, every equilateral triangle, or every semicircle, you still measured at least one and then worked either down from there or got bigger from there. So just to remind ourselves, we want to figure out how to figure out the height of a line, okay, under a curve. So, which is what you guys did, like when you were dealing with a triangle base, like, oh, look, there's your triangle base, and you measured it. Okay, so just to remind ourselves, we're going to work on measuring it. I know we, did it in Algebra 1, but we're going to review. So if I look at this first line here, okay, it's at 1, and I kept the height of it from the y-axis. So that height there is 1. This line here at 2, I'm going to get its height from the y-axis. Oh, look, it's also 2, and this one's going to be 3. Okay, and then same thing here. My line here has a height of 1. If I go to the y-axis, I have a height of 2. If I go to the y-axis again, I have a height of 4. Okay, it's not rocket science. So when we're dealing then with a general case where we don't have numbers that we look at, or we can't define our curve, when you have a height of, when you're at x on the x-axis, then your height is defined by whatever the f of x value of your curve. So in this case, it's not really 2. I don't know why I did that. Let's see if I can find my eraser. Okay, it's just below 2 if you look at that line and on your notes. So I don't want to estimate. I want to know the exact value. So I can figure out the exact value by plugging into f of x. So if we call this x1, this height here would be f of x1. Okay, remember, y is the same thing as x. You can think of your y-axis as your f of x axis. Okay, if you had another point, x2, whatever the height of that line would be defined by the function value at x2. Okay, a little review. So the way we figure out volumes, which we've talked about before, is we're going to look at the area of a cross-section. So the cross-sections are the shapes you put on your base. So for example, you could have had semicircle cross-sections, but your base was a triangle. Or you could have square cross-sections, but your base was a semicircle. Okay, so a cross-section, which we haven't even defined yet, but a cross-section is just a 2D slice of a 3D figure. Okay, so we took a volume shape. So there you go, you have a volume. And we just cut a line through it. Okay, so like if I were to cut whatever shape I just drew, I don't know, a vase looking thing in half, my cross section would be a circle. Okay, because it would be the slice of that figure creates a circle. So now if you look at your cross sections that you put on your base, they're not all the same size. Right? Some cross sections are bigger than others. All of your bases change size depending on where you are in your base. Like if you look at my triangle again, right? Like a cross section here is smaller than a cross section there, which is smaller than a cross section there. So they all change size. So we say a cross section, the size of a cross section depends on where they lie on the base, okay? Where it lies on the base. Whoa, that's the ugliest looking word base I've ever written, but we're just going to go with it. Okay, so just like the height of each of these lines depend on where it is on the x-axis, the height of your cross-section depends where it is on the base. Okay, makes sense? Like, look at the shapes you created. They all have a different size cross-section. Okay, or across the base as you work one way or the other. They're getting bigger or smaller, but they start off big and get smaller to both sides. So they are going to change because they can only be so big as the piece of the base they're sitting on. Oh, whoa, I don't know what I just touched. Okay, never mind, my menu came back, so I'm going to scroll on up. I should also mention that I'll be in here at lunch today if you have questions. I know I'm going kind of quick, so please write down questions. I'll happily answer them at lunch. So then we want to find the volume of a solid, okay? So the volume of a solid, its definition. The volume of a solid of a known integrable cross-section area, A of x, from A equals x to B equals x, is the integral of A from A to B. So just to make it really clear, integrable is a word, it's not a typo, okay? And it is a function that you're able to integrate, okay? So if I write this down using notation, I have the integral from A to B of the area of my cross-section, and I'm integrating it with respect to x, okay? Now, you guys have actually done that before. I'm just going to zoom in a little bit so I have some space to write. Whoa, this is going all over the place there. Okay. You don't need to put it in this box. I just am because I have space there. So when we were estimating the area of a curve, and we used rectangles to do that, we took the area of each rectangle and added them together, okay? And we said as the number of rectangles approaches infinity, their widths are going to approach 0. So say this curve was the function f of x, then we integrated from a to b, whatever that function is, times dx, okay? Now, we said that that is equal to the limit of the area of these rectangles as they approach infinity, or as the number of them approaches infinity. So you guys were actually taking cross sections before, right? We looked at a two-dimensional, whoa, that's not what I meant to do. We looked at where's my button? We looked at a two-dimensional shape, and in this case it happened to be a two-dimensional figure, okay? But that's what we're doing. We're gonna slice our volume so we can look at two-dimensional shapes and then integrate that to figure out the volume of the entire region, which is exactly what you guys were doing before. So we want to find the volume, so cross out the area of, because that makes no sense. We want to find the volume formed on the region, on the shaded region with square cross sections that have base xy and that have bases on the xy plane. Okay, so I want to figure out, here's my base. So what I always do is I draw the base of the cross section first, or the piece of the cross section I know first. So in this case, it tells me the cross sections are squares. Okay, so I'm just going to draw a square because I know that's my cross section. And its base, so like, I don't know if I call that my base, is on the xy plane. Okay, so this blue line here is the base of my cross section here. Okay, now that cross section is going to change, right? X, it's this height, but if I move it over here, it's bigger. If I move it down here, it's smaller. So I want to leave the height of my cross section in terms of x, okay? Because I want to integrate with respect to x. So if I look at my equation right here, I have x and y. That's not going to work for me. I need to solve for y. So when I do that, I'm going to get y equals negative 1/2 x plus 1, okay? So I know the height of this line then is negative 1/2 x plus 1, the same way that I knew the height of these lines were just whatever my f of x function was. Okay? So it's the same reasoning as you used up at the top of your sheet. So then I know that my base has a height of negative 1/2 x plus 1. And I know that since it's a square, its length or its width or whatever you were taught to call it is the same. Okay. So then I know that the area of my cross section is equal to the area of whatever this square is. And the area of a square is base times height. So that's going to give me negative 1/2 x plus 1 squared. Okay. So that's what I'm going to integrate. Now, if I look back at my figure, I know my bounds are going from 0 to 2. So that's what I'm going to put on the bounds of my integral. Okay, so I'm going to integrate from 0 to 2, a of x dx. And then I can just plug it in. So that's equal to the integral from 0 to 2 of negative 1/2 x plus 1 squared with respect to x. You can go ahead and solve that using u substitution because you have, whoa, an inside function. You can do that by hand. Please do not put it in your calculator. You are very capable of doing that by hand and figuring out the correct answer. So go ahead, pause the video if you need to, and do that now. Okay, so let's move on to example 2. Okay, so again, this has the same typo. So we don't want to find the area of the volume. That makes no sense. We want to find the volume formed on the shaded region with quarter circle cross sections that have diameters on the XY plane. Okay, so again, draw your cross section. So in this case, my cross section is going to be a quarter circle, right? If you were to extend it, it'd be a whole circle. We're only dealing with a quarter circle, and its diameter is on the XY plane. So keep in mind that even though we're dealing with a quarter circle here, it still is going to be a full diameter. So my diameter is actually going to go below my curve. Doesn't matter. I just want to deal with the piece that's above it, okay? And the piece that's above it is the radius that you need for this problem, okay? Now, again, using the same type of reasoning, that radius has the height of my function. So that radius has height negative x minus 3 squared plus 4, okay? So now I got to figure out the area of my cross section. So the area of my cross section, A of x, is pi r squared divided by 4, because I'm dealing with 1/4 of a circle. And my radius, again, is just my function, okay, because that's the height of it. So that's going to give me pi times negative x minus 3 squared plus 4 all over 4. Oops, I forgot to square my radius. There we go. Okay, so that's the area of my cross section. Okay, so then same thing, we're going to integrate that, and I know based on the bounds of my region, I'm going to integrate from 1 to 5 of the area of my cross section. So I'm just going to pull pi over 4 out to the outside because it's my constant, and I need to integrate negative x minus 3 squared plus 4 squared with respect to x. I highly recommend just either factoring this whole thing out first and then squaring it, or just, I don't even care, plug in your calculator. That one's kind of a pain to handle, okay? Okay, so make sure you have an answer here. Next problem. So in example 3, I wrote it out for you in words, so you just kind of have the idea of kind of the complicated nature of these problems when you have words that go along with it instead of a diagram. So in example 3, it says the solid lies between the planes, so the solid meaning the base, okay, lies between the planes perpendicular to the x-axis at x equals 1 and x equals negative 1. So, whoops, that's not what I meant to do. So I have an x-axis. At negative 1 and 1, I have planes. So my solid is in this region. That's what that first sentence tells me. Then it says, the cross sections are perpendicular to the x-axis. So I know that my cross sections are going to be perpendicular to the x-axis. And they're squares. So I'm just going to draw a square here because I know that's what I'm going to have to deal with. Whose diagonals run from the semicircles y equals negative the square root of 1 minus x squared to the semicircle of y equals the square root of 1 minus x squared. So those semicircles, if you put them together, just form a circle with a radius of 1. Okay, and so I'm going to extend this dotted line. Okay, now, it says in the problem that you're looking, the diagonals of the square are between the semicircles. So when you're looking at this picture then, this cross section that you drew is this diagonal of your square. Okay, so I'm going to actually just put in different colors so you can keep track of what's going on. So this cross section is this diagonal. Okay, now it's a circle, so it's symmetric, right? So the length of my cross section in this region is half the whole thing. So if I call that region x, and that length is the square root of 1 minus x squared, I would need to double it to get the whole thing, okay? So then that diagonal has the length of 2 times the square root of 1 minus x squared. Okay, now we need to figure out the area of my square. The area of my square does not depend on my diagonal. It depends on my side lengths of my square. So a square has 90-degree angles, so if you draw a diagonal, it cuts them in half. So this becomes 45 degrees, and this one also becomes 45 degrees. So we're going to take a trip back in time to geometry, where you learned about 45, no, the bell, 45, 45, 90 triangles. Okay, so my hypotenuse of this triangle corresponds to the diagonal of my square. Now, these triangles have the relationship of my side lengths, where this one's s, and the hypotenuse is s root 2. Okay, so I know that this function has to equal s root 2. Okay, so s root 2 is going to equal 2 times the square root of 1 minus x squared. When I solve for s, that is going to give me s is equal to 2 over root 2 times the square root of 1 minus x squared, which is my side length of my square. All of my first, 5th period students are walking in. Okay, so that's the side length of your square. So then the area of your cross section is that squared. Okay, and again, we're going to integrate that. So we need to integrate a of x with respect to x, and if you look back at your bounds, you're going to go from -1 to 1. Okay, so please go ahead and integrate that and figure out what your answer is. Now, just quickly, for number 4, your base is the same, but now you're dealing with equilateral triangles. So just a little hint, because you're going to do this one on your own. When you're dealing with equilateral triangles, your height for the formula, area... Can you guys stop talking for a second? Area equals 1/2 base times height. Your height has to be perpendicular to your base. So in this case, you're going to have to look back and remember, what do you know about a 30, 60, 90 triangle? Because it has a special relationship the same way this one has a special relationship. Okay? So you need to figure that one out on your own. Remember, I'll be in here at lunch if you need more help.